Next group is MCP for classical error correction.
Okay. So I ended up here because my friend Caesar pointed out the night before the application was due that this thing was going on. And he said, we need to sign up. So I signed up a team and I wrote down the first thing I thought I was just, make an LLM try and come up with error correcting codes. Over the past 24 hours, the team has slowly degraded, and it's now just me. But there were some interesting things that happened along the way. So one of the first things that we tried to test about the MCP is like, what's really its ability to reason? And we just did things that you do the first time you play with an LLM. So that we connected up an MCP, which was thinking of a hidden number. And what you can see here is that the MCP has spit out text back to the LLM, which tells it after it guessed the number 50, 50 is not greater than the hidden number. And the LLM concludes, so the hidden number is 50 or less. Let's try smaller. Okay. So if 50 is not greater than the hidden number, 50 is less than or equal to the hidden number. In other words, it's reasoned backwards. So in some sense, if you're going to hand the LLM some text, you should think carefully about how exactly you're telling it the information. Because as soon as you phrase it in a better way, if you don't say not, the LLM will recognize that 50 is in fact less than the hidden number. But when it sees the word greater, it's like, greater. Okay.
I think I might be an LLM.
I made the same mistake.
Yes, yes. No, so it's I was having a conversation with Xiaolong about this during the competition, and he said, this connects with this idea that LLMs are really all doing type 1 thinking, meaning like they are using working memory, short-term memory. And as we heard from our first speaker from OpenAI, whose name I can't remember right now, there's the part of the reason that you want to use MCPs is that it gives the LLM an ability to have a long-term memory and to check its logic in a verifiable way. So one of the ways that the LLM can verify its logic is using the language lean. So like, MCPs are technically developed by people outside of the company, but lean is a language that's used on all of these benchmarks that the LLM uses, right? So when the companies test their own LLMs, they've done reinforcement learning to make it better at writing lean programs. So now a brief intro to classical error correcting codes. Okay, so classical error correcting codes, you got data, you're sending it down a line, some of the bits get flipped. And we want to fix this, so we add some redundancy. And the usual way that you specify redundancy in so-called linear codes, which I'll explain why they're called linear codes in a second, is these three numbers. So it's the code length, the message length, and the minimum distance. So the code length is the number of logical bits that are going to appear in the data. The message length is the actual bit length of the messages, and the minimum distance, other way around. The code length is the length of the messages, is the length of the bit strings you're going to send down the line. The message length is the logical set of bits, and D is the minimum distance between code words. So you can specify a classical error correcting code with a generator matrix like this. And the way that it works is if I have a code word, I'm going to multiply it on the right by the generator matrix to make a message, which I'm going to send down the line. So once I get a message at the other end of the line, I'm going to use a parity check matrix. So this is just a matrix that is the remaining orthogonal vectors to this set of bit strings. And the reason that works, if you think about it, is because I've created something that is in the span. If you're thinking about this as a vector space over like F2, I've created a vector that's in the span of those vectors. So none of the code words should appear if I project it onto the orthogonal subspace. Okay, and here's an example of a generator and a parity check matrix. Okay, so basically what this is going to do is it's going to attach the LLM to this thing to a diagnostic for creating error channels and creating error correcting codes using generator matrices and let it test fidelities. And then it's also going to attach it to a lean proof checker. And it will try and use the things that it learns from playing around with the error correcting code to prove statements about the code. It also has these other useful tools when thinking about classical codes, which, you know, that's not really that important. Okay, anyway, so let's now. So one of the things that I also implemented was consistent state. So by default, when the MCP processes a request, it just sort of exists as a single request on the server. But this server will actually remember all of the error correcting codes and error channels that the LLM created during the conversation. So what I had hoped is to see it sort of do its own reasoning. But unfortunately, not during this particular demo, I mean, overall. But unfortunately, it has in its training data lots of stuff about classical error correcting codes. So you can see what it's going through is just like choosing standard options for this. I'm actually surprised that it didn't do the one that I'm thinking of yet. But yeah, so it's using the names for these, which I did not tell it. So it's just remembering this from the training data. Well, anyway, we'll go back and forth like this, and I can show an earlier example of playing around with it. So here, I have a channel that actually has a specific set of correlated bit flip errors, and it goes through and it tests several channels for correcting these bit flip errors, and looks at their fidelities and finds, you know, the best one out of the ones that it tried was this 6.2 code. Okay, yeah, that's my thing.
So it creates the code, and then what does it do?
So it creates the code and it creates an error channel. So in the example that I showed, I specified an error channel, and then it will test the fidelity of the code by sending code words through the error channel and seeing the percentage of the time that it's able to successfully recover the message. And then it will also try and prove that the thing that it's done is optimal and lean. Lean is like a proof checker. So I didn't write that though. Like there's already an MCP server for it writing proofs in lean. I could show an example of. Yeah. So there's like my server lets it do like numerical analysis, and it will spit out some known bounds that it can use while it's doing the numerical analysis. So like the sphere packing bound and things like that. And then it can use that to try and help it write the lean proof. Let me see if I have. So here we go. Well, okay, this is also not one word. Actually, yeah, so lean search is the MCP server for writing in lean. And then it saves, there's like a folder that I have here where it saves things that it's proved. Anyway.